So today I'm going to talk a little bit about why exploratory data analysis and looking into different characteristics of your data in different ways is a really valuable tool which really needs to be done before we jump straight in and try to do any clever statistical models or statistical analysis so that we do understand our data and we don't end up making stupid mistakes or overlooking very important characteristics. The data I'm going to use to kind of illustrate some of these points comes from the UK government, who every year release a report on the carbon emissions right down at different geographic levels, from national level all the way down to relatively small local authority level. Generally, kind of the publicly available reports look a little bit like this, which is on the screen at the moment, where they go in for the high level summaries of this particular data set. One of the nice things about this data, though, is absolutely anyone can go on the website and download 500,000 rows of data and dig into it in whatever way they want. So this is what I'm going to do today. And particularly the thing that I'm interested in exploring is trying to understand what sort of relationship exists between the area of different local authorities and what the level of carbon emissions is in those local authorities. It would make sense if there was some relationship where bigger local authorities had higher levels of carbon emissions, but I'm going to explore my data and try to understand exactly what the nature of this relationship is. So the very first thing that I'd needed to do once I downloaded my 500,000 rows of data from the UK government website was to summarize it into a format which I can work with. And this is kind of step zero of the exploratory data analysis process, is that data manipulation, data processing step, so that we've got the data just for 2022. And once we do have that data, we could just kind of scroll through and try and spot exactly what's going on in the data, identify any high values, low values, duplicates, weird things that have happened in that processing. With a large data set, you're going to get quickly overwhelmed trying to do that. Here, I've got one row for each local authority in the UK, so 361 rows. It's not going to take me too long to browse through the whole data set. If I do have raw data with 1,000,000 rows, 2,000,000 rows, 10,000,000 rows, it's absolutely going to be a waste of everyone's time to dig in and try and look at the raw data as just the data set. And this is where these exploratory methods, these visualization and summarization methods, are going to help reveal different aspects of the data and identify different specific values or specific characteristics of that data, which are worthy of more explanation. Generally speaking, the visualization methods for exploratory data analysis processes are far more important and far more powerful than the summary statistics. At this stage in the process, we don't care about estimation, we don't care about quantification of particular values. We care more about the general patterns and the general trends so that we can improve our estimation processes later on. And when we're considering what we're going to do here with our carbon emissions and our area variables, firstly, we're going to look at them kind of one by one to try and spot the patterns, spot the distribution of each of the variables, how much variability is there, what's the shape of the distribution, are there any odd looking values, is there anything we're seeing which doesn't make sense as we try and link it to our own knowledge about those particular quantities. And so at the moment on the screen, I'm looking at a histogram of the CO2 emissions at local authority level. And a histogram is a very nice way of summarizing the data to see the trend and the shape. It's a little hard to infer directly any sort of specific summaries. We can't read off a histogram, for example, the average or any form of median or mean, or even what the standard deviation is or anything like this. But we get a good idea of the spread and the variability in our data. We can see there's a very small number of counties with quite low levels of emissions, and it quickly goes up to where the majority of emissions are. And then there's this slow tail way down to a very small number with very high levels of emissions. And what histograms do is they take a continuous numeric variable, like the carbon emissions, and group it together so that we group everything between 0 and 100 and then take a frequency, then everything from 100 to 200, 300 to 400, and so on. This kind of definition of how we draw the bins, how wide we draw those bins, I've taken whatever the default options are here in R to draw this. It may not be that sensible. I can tell looking at it, it's not as nice as having 100 by 100 by 100. And it's a little bit subjective in terms of how you decide what the correct width is, how many bars to draw in a histogram. And so this is where you also perhaps would see a density plot, which smooths out those histograms and gives you a better idea of the shape in a slightly less subjective way. The difficulty here, though, is then we almost remove the way to directly link this visualization from the data. Knowing that the density of the distribution is 0.001 at a value of 300, we're a little bit abstract in terms of trying to understand how this links to the data, but we get a much better idea of the shape of the data. And this is kind of a key thing to consider with all these different options for visualizing data. You're going to have some different ways of summarizing it, which give the trade-off between displaying the data and summarizing the data. And to go to the extreme end, you might just do a scatter plot with just one variable. So each point here is all in a line for every single observation in our data set. This is very much displaying our data. We're not really able to see anything about the shape. We're not really able to see anything about where the average value may be. But what we could see here is some of the specific higher values. This would be a good way of spotting potential outlying points and identifying where those come from. And I can see from hovering over, my outlying points for emissions here come from Birmingham and North Yorkshire. I kind of know Birmingham, very highly populated urban area, North Yorkshire, a very large area. It's not too surprising that these would be high levels of carbon emissions. When we're thinking about these kind of outlying points, we always want to be considering, do we believe these are real points? How far out of line are they? If this was a value of 10,000 kilotons of carbon, I would be suspicious that there could be issues with how the data was collected or compiled or processed. Here, they're not really that much higher than the other points that we have. And logically, we can link to other variables. In this case, I've done it based on my own knowledge, but there may be other variables in the data to quantify the size and quantify the population, which we do have in the data, and we'll look at later, to explain why some of those points might be higher. So just because you see an outlying point doesn't mean it's a problem, but it means we want to keep that in mind and consider what it is. And it could be a problem if it is very much out of line and there is no explanation for how far out of line it could be. So I've taken a look at my CO2 variable. I'm relatively happy with the range of values that I've got. I've got a nice distribution with some low, lots in the middle, a couple of high values to maybe be considering what I should do with them. Nothing's jumping out here at me as being a particular problem when I go through my different visualization options. If I move to my area variable, though, it starts to look a little bit different. Just from my scatter plot, I can see I've got 1 point way off in the distance, and then nearly all of my data is clustered down here. And in fact, if I go from a scatter plot to a histogram, I can see it's perhaps even worse than I initially thought in terms of how clustered my data is towards the lower end. Most of my values get put in this very first bin in my histogram. I've got one value way off in the distance. Now, I might be thinking, have I added an extra 0 at the end of the area? Is there some mistake in the calculation? If I go back to the scatter plot to identify it, I will see this is the Highlands of Scotland. And I know that this is a local authority, which is absolutely huge. And it kind of makes sense now why there is that 1 point way off in the distance. But that sort of distribution that I'm seeing, if I go back to my histogram, this is going to cause problems for analysis if I just treat area as the variable by itself right now. If I don't do anything, I won't really be able to get any kind of understanding of the variability that exists within 90% of my data. It will only really be the trends which are pulled out by these very high values. These will become a very high leverage points in any statistical model that I would try to fit. And if you see a shape of a distribution which looks like this, starting very high, flattening off, and then going out to a very low number of very high values. This is the classic case where you might be considering a log transformation of your variable. And this converts the way of thinking about that variable of, let's not think of increasing area by 1 unit at a time or by 100 units at a time. Let's think of increasing it by a particular factor each time. Let's think about doubling the area or increasing the area by a factor of 10. So on my axis now, instead of going from 10,000 to 20,000 to 30,000, I'm going from 10 to 100 to 1,000 to 10,000. And as if by magic, when I turn my area into a variable plotted on the log scale, I get an almost perfect symmetrical distribution, starting low, going higher, going down low again. My Highlands of Scotland no longer really looks like such an outlier where I am considering this variable on the log scale. And so there's lots of different transformations you might consider. It's usually a good idea to consider, though, what the implications of doing that transformation is. A log transformation can nearly always be justified for most variables as long as we switch our brain to thinking about the change in rates rather than the change in per unit change. Often you'll see people who try and go for kind of data-driven transformations, and we'll look at, what makes our distribution look the most perfectly symmetrical and have the most amount of variability spread across the full range, and let's go with a very arbitrary formula for transformation. And that's going to cause problems with the interpretability and usability and the link to the scientific theory and the real world applications of what you're doing to that variable. So there's certain contexts where there are transformations that will be known to have scientific validity for that particular context, but do think carefully about going for a purely data-driven approach at this point. However, I can quite clearly see that this log transformation is going to work pretty well for giving me that nice spread in the data and that nice range of values in the data for my area variable, where I'm no longer going to be particularly worried about what's going to happen if I choose to use this variable in a statistical model. So I've looked a little bit at the variability in the carbon emissions, a little bit about the variability in the area. I haven't exhausted all the possible sorts of data visualizations that are out there. I've just zoomed in a little bit here to some of the key things which I know are problematic with this particular data set. One of the important things about exploratory data analysis is to be willing to try lots of different ways of exploring the data and trying lots of different visualization methods. Some of them may not tell you very much. Some of them may end up being quite valuable. And always keep in mind this trade-off between displaying and summarizing. One end of the extreme of that scale, you could just choose to plot a mean value of the area. Maybe you may even put the mean value split by country to just have a bit of a comparison. This is not going to tell you that much about the data itself by looking at the variables in this way and only focusing on the mean values. The purpose of doing the exploratory data analysis is to try to get a better understanding of the full range of the distribution and the variability. So yes, this helps us to see that local authorities in Scotland are larger on average compared to the other counties. But if I chose to look at this through a box plot, for example, I actually see that in Scotland, the reason those values are higher is more to do with the maximum value. It's not that the whole distribution is generally shifted upwards. It is a little bit compared to England, but it's not so much compared to Northern Ireland and to Wales. And this is perhaps where box plots become a more useful tool for making comparisons compared to looking at overlaying histograms or overlaying density plots or violin plots. I tend to find box plots are a good way of comparing different groups to each other. And in this case, it's highlighting to me that, okay, on average, my local authorities in England do look to be a little bit smaller than in my other 3 counties. If I'd have tried to look at this through just plotting the means, yes, I can come back and now see that England is indeed the lowest mean. My eyes more got drawn towards the fact that Scotland had a higher mean value. And actually, that possibly wasn't the more important thing to be picking up. And similarly, if I'd looked at, say, violin plots, So violin plots take our density plot and mirror it. And this is another alternative for being able to compare the distribution across our different groups. This shows us a shape of the distribution across the 4 different groups, but it's harder to pick out, okay, what is the difference in the average between those 4 countries of the UK. And the box plots kind of visually help make that comparison across groups a little bit easier. So the main thing that I'm really interested in getting to now, though, is being able to look at the direct relationship between the area variable and the CO2 variable. And in this case, I would be comparing 2 numeric variables to each other. And this is the perfect scenario for where we want to do a scatter plot. So I'm going to put my area on my x-axis, and I'm going to put my CO2 emissions on my y-axis, and make a nice scatter plot. And let's start out with no transformations just to see how this looks, because looking at my scatter plot of area versus CO2 emissions, everything gets squashed into this bottom left-hand corner, and it's very hard to work out any sort of relationship at all between the variables. I might be tempted to try and overlay a trend line onto this particular scatter plot just to get a visual idea of, is there a trend? Because I can't really tell right now. And this issue of having a high leverage point when I try and draw on my smooth trend really comes into focus, because maybe here in my small cloud of points, oh, hang on, there's a line going up, could be something interesting happening. But about 95% of my screen is drawn up with a trend which is more or less entirely being driven by this point up here and this point over here in terms of how it's choosing to interpolate that trend. So this is kind of nonsensical as a way of trying to kind of summarize this particular relationship. If I take that off and do my log transformation of the area, suddenly my scatter plot looks completely different. Now I've got a nice range of values out on my x-axis, and even before I draw the trend line, I've now got enough visual information to start inferring, is there a pattern? Is there not a pattern? And maybe, I think, is the answer from trying to look at it. There certainly seems like some of the points at the higher end of area do seem to have higher emissions. Maybe in this big range of the majority of my points here, the trend is a bit less apparent. I can again overlay my trend line. And as part of the exploratory process, it's a good idea to use trend lines which are a kind of smooth trend, a moving average trend, rather than a quantified linear model or quadratic model, just because that helps you to understand the nature of the relationship, again, in a slightly more objective way, rather than overlaying, is it a linear straight line? We may decide that it's close to a straight line, and that will work for later. But at this point of exploring, we want to know, okay, is it something with curvature? Is it something which has segmented trends where it starts flat and then increases? Is it something which is kind of an S-shaped curve? At the moment, when I'm looking at this, it looks indeed to be relatively flat, up to the range of about 1,000 kilometers on my log scale. And then as I'm increasing further beyond that, there does seem to be some evidence of this relationship between my 2 variables. But the nice thing about scatter plots is we can start customizing it and adding in a lot more than just 2 variables. So I've mentioned already when I was talking about Birmingham, which is one of the most populous counties in the UK, this point up here jumps out quite a lot because it seems to be quite a big outlier from the trend. It's not a very large county, but it is a very populous county. So perhaps we can start incorporating some other variables into our data. So within the data that I brought down, I also have the population of each local authority. And so I can size my points so that the bigger points are now going to be the points which have the highest amounts of population. And something to me then immediately jumps out from this particular plot. If you look at the points above the red line, above this general trend line, these are the bigger points. These are the ones with higher emissions than expected from the overall trend. And if I look below the line, it's the smaller points. And these are the ones with lower emissions than you'd expect from the general trend between area and CO2 emissions. And I think this is telling me quite strongly that I can't really consider this relationship between area and the CO2 emissions without also considering this factor of population within my unit, which is the local authorities of the UK. And in fact, if you look at any of the government publications, how they always deal with the CO2 emissions is very rarely in the kilotons. They adjust it for the population. So it's kilotons of CO2 per capita. And so I think I'm also going to make a transformation here on my y-axis, but this one is going to be based on the population. So I'm going to convert this per capita. And that's perhaps not the trend that you were expecting to see when I did that, because something very odd has now happened when I've converted my CO2 to CO2 per capita. And again, it looks like we have one outlying point. So let's take a little step back to go back to a histogram of just the CO2 per capita. And here we can see we've got a very nice squashed distribution here where nearly all of my counties are when I'm looking at CO2 per capita. And then one strange point off in the distance here. If I go back to my scatter plots and bring back area, here if I hover over it, you can see this is the City of London. And actually now in this case, I'm starting to think the City of London, this could be a real outlier that I do want to remove from my analysis. And the reason I would say that is because the City of London, it has a population of around 10,000 people, but the number of people who work in the City of London is 500,000 people. So if we're trying to understand the impact of CO2 per capita, the City of London it's not the whole City of London, depending on your knowledge of UK counties. It's a very small area within London, which is the main financial and business district, where 500,000 people come in to commute every day. None of the other counties of the UK have this strange property that the City of London has, where far more people spend time there, commute there, emit carbon there, than actually live there. Ideally, at this point, I would be thinking, do I have another data source I can merge in to help explain why this is much higher? And probably a data source to do with employment numbers or economic numbers for how many people and how much industry there is in a particular local authority. And that could start to explain why the CO2 per capita is so much higher in the City of London than it is from the rest of the counties. But I think what I am going to do here is say that for the purpose of my analysis, I don't think that I should be including the City of London in an analysis of CO2 per capita versus area at the local authority level. So I am going to go into my data a little bit and delete the City of London. So I've removed one row from my data and then see how that affects my scatter plot. And you can see I've suddenly zoomed right in to having a nice range on my y-axis again. I'm no longer squashed right at the bottom. And I can see generally a much stronger trend than I have seen in any of my other plots so far. I've got a nice consistent increase, which maybe flattens out at the top and maybe flattens out a little bit at the bottom. But for the majority of my range, I've got a pretty strong relationship where as I increase the area, as I increase the increase in area, because I have it on the log scale, I'm increasing my CO2 emissions per capita. And it's no longer such a clear trend that the large counties are above and the small counties are below the line as it was before I did my transformation to the y-axis. Perhaps a final thing to consider here is, should I be modeling this when I go to my next stage as a curve, as a straight line, as a segmented regression, or should I be bringing in other factors that could perhaps explain this curvature? So I've looked at modifying size. The other thing I can modify is the color. So maybe if I bring in a different color for the different regions. So I've got different regions of the UK. And if I look down at my low levels, I can see that all of these points at the end of my scale here, and particularly these points above the line, which are causing this trend to kick up a little bit for the small areas. This is London. This is Westminster and Kensington and Chelsea and Camden. So it's not just the City of London, which is causing some problems, perhaps, with the shape of the trend. Not necessarily problems here for these 3 points, because it's within reasonable range of the others. But perhaps it is something similar where more people are commuting into these areas for work than actually live there. So this is making me think perhaps I want to include a variable to account for that. Perhaps in my model, I do want to include a variable which captures these different effects of the different regions. Because in London particularly, it looks like something odd is happening. Nothing else is jumping out immediately from the other counties, but this might be something I want to explore in a bit more detail when I go into the different regions, try to understand if there is different clusters or different patterns where things may be operating differently. It could be more than just London, it could be an urban-rural effect, for example, which is something I would be really wanting to capture and understand how this relates to that link between area and CO2 emissions. So this is not the end of my analysis process. This is really just the start of my analysis process, where I've done these initial explorations so that when I come to fit statistical models and test hypotheses, I'm going to be doing that from a much more informed position about this relationship between area and CO2. I'm not sure exactly what form of model it will take. It could be something curved. It could be that allowing certain covariates will help to explain this curvature, and a more straightforward linear regression model may be a perfectly good fit as I go to explore it. But this particular starting point, where I've made my transformations and I've adjusted for per capita effect of CO2, and I've looked at the effect of population and region, all those things I've looked at along the way have really helped me get a better starting point than this, where if I took in the trend line, I have an incredibly useless, misleading trend. If I take out the trend line, I've got no idea what the relationship between these two variables actually is. And I'm tempted to throw out the Highlands of Scotland because it looks so different to everywhere else. And that's not a good basis for a model between these two particular variables. And this process of trying out different things and exploring the data in different ways is really going to help you get a good feel and get a good understanding of what the relationships look like in your data, whether there are any points or aspects of the distribution that need to be accounted for as you move into those next steps. It's also going to highlight errors with your data cleanliness and data processing. In this particular case, it was a publicly available government data source, so it would have been a little bit surprising if I'd have come across any major data errors within there. Definitely not impossible, but unlikely given how robust the checks would be on that particular data set. But for your own research and for perhaps less used public data sets, a lot of errors can creep in, and this process of exploring that data may uncover some major issues with that particular data set. And equally, if you've done data processing steps to get to this starting point, you may have made a mistake in how you aggregated the data or derived particular variables, which would become much clearer through this exploration process and understanding the variability in those variables, compared to if you had just dived straight into using those in a particular analysis.